Hey guys, what's up? Welcome back to the classroom. It's Mr. Low, and today we're just gonna go through a very quick topic, chapter 3, force and pressure. Right, so the concepts here in this chapter, you've kind of seen it before in lower sec, particularly sec 2. There's nothing much very new, so I will just quickly go through all these concepts. Yeah. Okay, so quick one at the start. Okay, so when you talk about science and history, the concept of density and buoyancy was found by this guy by the name of Archimedes. So what happened was, the story goes like this, right? He was tasked by the king to find out whether the king's crown was made of pure gold, or was it mixed with some other cheap metal like silver or whatever, right? Clearly he could not break the crown to see what's going on inside, right? So after thinking for very long in a bathtub, he suddenly had an inspiration, right? Of how to decide whether that crown is made of pure gold, and he started shouting "Eureka, Eureka!" and comically he ran out of the bath completely naked because he was so excited to present his idea to the king, right? And everything in this story has to do with what you're going to learn today in this video, so we're going to check it out later, right? But first up, the very first concept that we need to know is the difference between mass and weight. You've already seen this in your sec 2, right? So let's just quickly recap again. Mass is the amount of matter, right? So we're looking at how much stuff, loosely speaking, how much stuff there are inside a body, and it's measured in kg. This is the SI unit for mass. Okay, but on the other hand, weight is another word for the gravitational force acting on an object, right? So they're very different stuff. Mass is the amount of matter, while weight is actually a force, in particular gravitational force. Since all forces are measured in newtons, right, as their SI units, so does weight, right? So the unit of weight is newtons. Okay, so let's move on from there. We'll skip this page for now. The relationship between the mass and weight of an object is given by this formula, W equals to mg, which you should have seen this before, right? So W is the weight of an object, mass, M for mass, and this G is actually called gravitational field strength. Gravitational field strength. Now this gravitational field strength, loosely speaking, is just how strong gravity is at a particular location. Yeah, so if you're on Earth, it's a certain number. If you go to the moon, it's a totally different number. It depends on the size of the star or planet in terms of mass. So the more massive the planet or the star is, the stronger the gravitational field strength that planet or star or whatever celestial objects out there in the universe exerts on objects nearby. Yeah. So weight, as mentioned just now, is measured in newtons, right? The only thing here that may be new to you is that the gravitational field strength G is measured in newtons per kilogram. Right, in case you forget in an exam, how do we obtain this units, Newton per kilogram? Let's do a little bit of quick algebra. From W equals to mg, we can massage the equation to give us G equals to W over M. Since W, or weight, is measured in newtons and M is measured in kilograms, therefore we have G measured in newtons per kilogram. Yeah, so the unit of G is, I'm using square brackets to represent units. Yeah, so the unit of G is as good as the units of weight divided by the units of M, which is Newton divided by kilogram. Hence, you have your Newton per kilogram. Right, this is something that we learned in chapter 1, how to get the units of a not base quantities but composite quantities. Okay, so let's move on from here. So anyways, the gravitational field strength represents how much gravitational force acting on 1 kg of mass, right? So 1 Newton per kg, you can write it down at the side here. 1 Newton per kg is just represents 1 Newton of gravitational force every 1 kg of mass. Yeah. Okay, so it's the gravitational force acting per unit mass. So when we say per unit, actually we mean 1. This per unit actually means 1. And since mass is measured in kg, it just means 1 kg of mass. Okay, so every time you see this per unit, we are looking at 1 with the unit of the SI unit of that quantity. Yeah. So as mentioned just now, the field strength in the region you're at, in the exact location that you're at in space, it depends on the celestial object, right? The star or the planet or the galaxy that's near you, right? They create this gravitational field, and each of them has a different field strength depending on how massive these objects are, right? So you can see that on Earth is a nice number 10, right? And Moon is actually about 1/6 of Earth, so hence we round it off to 1.67. The Sun is way more massive than the Earth, hence the value is greater. So for ladies, just as a joke, if you want to feel lighter, if you want to be lighter in terms of weight, go to the Moon. Don't be on Earth. But we know that it's a lie, right? Because mass is always the same wherever you go. This you may recall from your lower sec stuff. Okay, so this number 10, right? This G equals to 10 for Earth. You may recall from the previous topic of kinematics that, hey, this number 10 also means the gravitational acceleration. That means any object that falls freely under gravity near the surface of the Earth would accelerate towards the ground at approximately 10. We know that the real number is about 9.8, 9.7, so on and so forth. But for your syllabus sake, we would just use the nice number 10. So this gravitational acceleration, which we knew from previous topic, the previous chapter, is also the same concept as gravitational field strength, which we generally use the letter G to represent. Okay, so this letter G here can mean the field strength for the purpose of calculating force. It can also mean the gravitational acceleration for the purpose of calculating speeds and whatnot in kinematics. Yeah, they kind of mean the same thing. But of course, the difference here would be the units, right? So this Newton per kg tells us it's about the field strength. But this meter per second square, we know is an acceleration unit. So the units would kind of tell us what we are actually looking at, but the number is the same. Okay, all right. So just now I mentioned about this thing called gravitational field. Basically, it is a region of space where a mass experiences a force due to gravity, or rather gravitational acceleration. So it is a region of space. So surrounding Earth, right, any planet actually, there is a field created because of its mass, and this field is what we call gravitational field. So if I place an object, let me just use something blue, right? If I place an object nearby the planet in the gravitational field, it would experience a force, right? And this force here is force gravity. I use a subscript G to represent gravitational force. Yeah, so yeah, this is what it is, right? If you have a field, a gravitational field in particular, and you place an object that a test mass object, any object that has mass, you put it there, it would experience a force, which is gravitational force because of the field. Yeah, so this is what gravitational field is all about, right? Okay, so we move on to an example. Okay, so this is a little bit difficult. So let's read the question bit by bit. Yeah, an object is dropped from rest. So again, if you do enough practice from kinematics, you would be sensitive about this word. Rest just tells us that the initial speed u is 0, right? Why I use the letter u? Because recall the formula a equals to v minus u over t. That's what I'm thinking, right? Drop from rest. Yeah, from the top of a cliff, the object falls for 5 seconds, and this is the t, the value of t. Notice how I write down the letter, right? So later when I need to use these numbers in a formula, I know exactly where to find the information. Yeah. Okay, ignoring air resistance, which is usually the case in the questions unless stated otherwise, sketch the speed time graph of the object and include any initial and final values of the speed. So this is something that you've seen in your previous previous chapter, right? Remember the power of speed time graph, it can give you a lot of information. So let me just quickly do my sketch over here. Yeah, let me draw in the axis, not forgetting the to label. So speed in terms of meter per second and time in terms of seconds, right? So the question here is to sketch the graph. So we need to know, definitely at the starting speed is 0, so we have 1 point over here. We need to find out what is the speed at 5 seconds. So this is something that we already learned. We can use the formula A equals to V minus U over T. Now in this case, special case, because the acceleration is due to gravitation and nothing else, there's no air resistance, we can simply replace A by G, which is, we know for Earth is 10, right? So in this case, I'm simply replacing A by the letter G to show that it is gravitational acceleration, right? V we do not know, which is what we kind of want, but we know that the U is 0 and T we do know, which is 5. Yeah, so in this case, the G we can replace it with 10, no problem, because we know it's gravitational acceleration on Earth or near Earth, right? So from here we know that the V is 50 meter per second, and we have our final value on our speed time graph, velocity time graph, 50, right? So draw a dotted line up as usual, just like kind of like plotting a graph, right? And yeah, because gravitational acceleration is a constant, yeah, so we know that this is a constant acceleration kind of graph, aka straight line, and we're done, right? So this example is really related to the previous chapter, kinematics, but here we are emphasizing that this acceleration for gravity is 10. Okay, now the difference between mass and weight, not just in the form of the definition that we discussed earlier, but also the way it's measured and whether is it location dependent. These are also very important stuff. You have seen this in your lower sec textbook as well, so I will not talk so much. Yeah, mainly the concept here is mass does not change with location. So this is why just now I say going to moon feels lighter, but actually, yeah, your mass is still kind of the same. It doesn't make you any slimmer or whatever. Okay, yeah, so let's try here. Okay, Alice has a mass of 50 kg, so as usual I'm gonna label my information. What is her mass and weight on the moon, knowing that the moon has a field strength of 1.6. Yeah, so for the first part, the mass and weight, we know that mass does not change wherever you go. So outright, you can just pop in the answer 50 kg without any form of calculation done. But for weight, well, we have to plug in the basic formula, W equals mg, and we use 50 as the mass because that's Alice's mass, and we use moon's gravitational field strength times 1.6, which gives you 80 newtons, and then we have the answer as 80 newtons. Right, very, very basic question, one step and you're done. Okay, now next up, okay, so this is a little bit tricky. It's got to do with the electronic balance. Right? So Bob steps on the electronic balance calibrated to Earth's field strength. It shows a reading of 70 kg. By the way, have you wondered if there is a difference between mass and weight, right? Mass is measured in kg and weight is measured in newtons. When you step on the electronic balance, do you think it measures mass or weight? Take a pause to think about it. Well, the answer actually, it measures weight, you see. Alright, let me draw you a simple picture to illustrate. You have your electronic balance here, and yeah, there you are standing on it, right? Okay, what exactly does it measure? Well, actually, it measures a force exerted on it, which in this case actually is the weight, is your weight, right? So what this electronic balance actually senses from you is actually your weight. So how is it that it returns you your mass, for example, 50 kg? How does it measures a force. How does it return you a mass, which is your mass, right? So the quick answer is this: because all your electronic balances or any weighing scale has been calibrated to Earth's field strength, right? So what it does is, whatever force it receives, it automatically divides by 10 and returns you the number, right? So in this case, in this hypothetical scenario that I just drew, the weight of the person should be 500 newtons, remember, times 10, yeah? So when the electronic balance receives a force of 500 newtons, it automatically divides by 10 to return you the mass of 50 kg. Now this divide by 10 is actually because of Earth's G, right? Because of Earth gravitational field strength, right? So with that, we actually can tell what is the mass of, sorry, the weight of Bob, you see. So here we have the mass, but we can calculate the weights later. What would the reading on the same electronic balance be if, sorry, no Peter, right? No more Peter, but Bob, okay, step onto it while on the moon, right? So the same electronic balance, he brings it to the moon and he steps on it. Do you think it would register the same 50 kg, sorry, no, the same 70 kg, or a completely different mass reading altogether? Well, common sense would tell you, not say common sense, yeah, but if you think about it, right, since the electronic balance actually measures a weight, a force, you know that on moon the weight is going to be smaller, hence it's going to receive a smaller force, right? But what kind of mass reading is going to return you? So this is what we're going to calculate here. Okay, but first you can take a pause of this video and try it for yourself, yeah? Okay, sorry, so we first calculate the weight of Bob, right? Which W equals mg, 70 times. In this case, we have to use 10. Why? Because this 70 kg is obtained on Earth, alright, and that gives you 700 newtons. That is Bob's weight, okay? Now, when he goes to moon, okay, I'm gonna use green for Earth and maybe black for, sorry, and black for moon, okay? Right, so when he goes to the moon, on the moon, okay, let's see. So the previous case is for on Earth, yeah? So on Earth, this is what happens, right? The electronic balance receives a force of 700 newtons divided by 10 and returns 70 kg. Okay, now on the moon, what happens is the weight is now different. W equals to mg. Now the mass is still the same, right? So that's Bob's mass, which is 70 kg. Now you have to multiply it by the g on the moon, which is 1.6. All right, so with that, you get, what's the number? 70 times 1.6, just give me a moment. 70 times 1.6, you get 112, right? Okay, so you get 112 newtons. Sorry, what's with the decimal place? 112 newtons. So the electronic balance receives a force of 112 newtons, but remember, it is calibrated to Earth's field strength. So it will automatically divide by 10 to return the mass reading of 112 divided by 10. And that gives me 11.2 kg. 11.2 kg. So my answer is erroneous, actually 11.2. Pardon my mental calculation. Yeah, so you can see that, oh, okay, Bob's mass on Earth, on the moon, suddenly has become 11.2 kg, but we do know that mass actually remains the same wherever you go. It's just that this mass reading is because of the fact that the electronic balance receives weight, a force, and divides it by 10 by default, no matter what, yeah? So this is why, yeah, it kind of appear lighter when you're on moon. Okay, so let's move on from here. Part 2, we have density, right? So in this section, yeah, density is something that you've already known very well. It is, by definition, it is the mass per unit volume. In case I forgot to emphasize, anything between the two blue bars is the definition. So please commit this to memory word for word. We may ask you what is the meaning of density, and you're supposed to just vomit this line out. Okay, so density, in your lower sec, I don't know what your teacher taught you, but over here you use the symbol called rho. Okay, so this is a Greek symbol. It's pronounced as rho, R-H-O. And how do I write it? Okay, it's not a P. Please don't be confused. So I start off from the bottom and I curve it up. Alright, so this is how you write the Greek letter rho. Why are we using Greek letter? Because we ran out of English alphabets. Yeah, physicists run out of alphabets to use. Yeah, so this is density, of course. But of course, welcome to use capital D for instead of rho if you don't like it. No problem. And it's mass over volume. This is something that you already know, right? This is why it's defined as mass per unit volume. Mass divided by volume. Okay, so the SI unit, of course, is kg per meter cube because mass is measured in kg, volume is measured in meter cube, so on and so forth. Right, let's move on from here. Okay, so to help you to understand the formula, how does mass and volume impact density? I have this simple example over here. Yeah, so let's take a look. Okay, the table shows 3 identical cubes, boxes, each with sides 1 meter. Alright, so this is a cube, and each side is 1 meter, 1 meter by 1 meter. Right, so they each contain different number of metal balls, each with mass 1 kg. So each of this metal ball has a mass of 1 kilogram. Right, and your task is to fill up the total mass, volume, density, and check the box with the highest density. Right, each of this box has sides of 1 meter. So to find the volume, you know that volume is length times breadth times height, so on and so forth, right? So 1 meter by 1 meter by 1 meter, and that gives you 1 meter cube. Right, in this case, yeah, the volume is the same for all 3 boxes, hence I can just duplicate in this case. Right, but the total mass in each box is different because, well, the number of balls are different. Right, so in box 1, you have only 1 ball, each of them is 1 kg, hence the mass in the box is just 1 kg. For box 2, you have 1, 2, 3, 4 kg. Here you have 1, 2, 3, 4, 5, 6 kg. Okay, now from there you can then calculate the density, recalling that density is mass over volume. You will take the total mass divided by the total volume, which in this case you get 1 kg per meter cube, 4 kg per meter cube, and last but not least 6 kg per meter cube. And of course, the one with the highest density is the third box. What is this trying to tell you? This example is trying to tell you that if I have the same volume and I change the mass, right, the density is going to change. Right? In particular, if you look at the formula itself, density equals to mass over volume. Here, what we're doing here is we are keeping volume constant, but we are changing the mass, in this case increasing. From there, density will increase. Yeah, because you're dividing a bigger number by the same number at the denominator. Good? Alright, let's move on here. In the second case, we keep the number of balls inside the same, which is we're trying to keep the mass the same, but we are changing the volume of the box. So without doing any calculation, which of this box has the highest density and why? Right, so we recall the formula to answer this. Usually in your explanation question, it will be good to have some form of formulas, right? So let's recall over here. We are using density equals to mass over volume. In this case, what are we keeping the same? We are keeping the mass the same because all of them have 2 balls, right? So we're keeping the mass the same, but we are increasing the volume from D to F. So volume is going up, right? Now, so when you divide the same number by a larger denominator, what happens is, well, the density will go down, right? So this is what the question is asking over here. So which one has the highest density? Answer is box D, right? Box D. And why is that so? Okay, while all of them, all the boxes have the same mass, well, all the boxes have the same mass, we note that box D has the smallest volume. Right, by, this is when you quote the formula, right? By density equals to mass over volume, the smallest volume will result in the greatest density. Ergo, D, box D. Yeah, so these two examples here, we are playing with different, in the first case, we're playing with different masses, same volume, but in the second case, we're playing with the same mass, but different volumes, and we see how density changes with it, right? So you can see that in your physics career 2 years here, you will see that actually most of the formulas, 80 to 90% of them actually fall under this kind of category, A equals to B over C. And if you're familiar with how the denominator and the numerator affects the final quantity on the left hand side, then you're good to go, right? You can manipulate things easily. Okay, so for different materials, clearly we have different densities, right? So some objects, some materials float on water, some sink in water, right? So it can be kind of used like a fingerprint, right? So if I can find the density of an object, I can kind of match it to one of the materials, and hopefully and kind of conclude that, okay, the object is made of that material. Of course, you can have more than one material having the same density, of course, yeah. So it just gives you a rough guide, yeah. So but either ways, if we have one fixed pure substance, so not a mixture, it can be a compound, of course. Here I'm just giving elements, but compounds, if they are pure, i.e. not a mixture, it does have a fixed density, of course, right? So the thing here is to take note is that any object with a uniform material always have the same energy no matter what size. Okay, so this is a trick question that often comes out. If I chop a piece of iron into 20 pieces of different sizes or same size, doesn't matter, how would the density of each small piece be compared to the original piece? Well, some of us may think that, okay, I've chopped it into 20, I divide the density by 20. But actually no, because simply said, it's still the same material. Each small piece will have the same density as the original big piece, right? It cannot be that I have a piece of iron that sinks in water. Once I chop it into 100 pieces, suddenly all the 100 pieces start floating. It doesn't make sense, right? Density will not change because it's the same material, right? So yeah, this is something that you already know. If the object has high density than liquid, it sinks. Not just liquid, maybe gas as well. Lower density, it floats. Okay? So over here we have a quick example, a cube. So I'm using a cube here because length times breadth times height, it's the same number. They have the length of 0.5, so you can calculate the volume immediately, right? And it has a mass of 192.5 kg. What is this material made of? If you look at the table in the previous page, so first we calculate the volume, length times breadth times height, you get this number. You divide mass by it, you get 1540, and you compare, not the previous page, in this page, so you compare 1540, you go to the table and you find, okay, calcium, and we have it. This cube is made of calcium. Okay, the final example over here, what is the volume of a piece of 100 grams of carbon? So in this question, I did not give you the density. You have to go back to the table here and find carbon has a mass of 2,200 kg per meter cube. Why did I emphasize this kg? You will see later. Okay, so carbon density is 200 kg per meter cube. Okay, so why did I emphasize the kg? Well, by now I hope you should be conscious enough to see the difference in the units given. Alright, so yeah, so first thing I note that I have to bear in mind that I have to go and convert this mass to kg, right? And in case you kind of forgot how to convert, 1 gram, okay, I start with 1 kg first. 1 kg is 1000 grams, right? Okay, so most of us kind of forget, do I divide or do I multiply by 1000? So here it goes. 1 kg is 1000 gram, right? So how do I get 1 gram? Well, I divide by 1000. Therefore, on the other side, I must also divide by 1000. Okay, so this in terms of kg is 1 over 1000 kilograms. Alright, so 1 gram is 1 over 1000 kilograms. As to what is the decimal, you can press your calculator, doesn't matter, right? So here I note that the mass in terms of kg is 100 divided by 1000, which gives me 0.1 kg. Right, so the question asks for what is the volume. Volume is the question mark. So I write down the formula first. Density is mass over volume. If your algebra is good, you can immediately massage the equation to give me mass over density to find volume. Yeah. Otherwise, if you're not confident, tip is you can always substitute the numbers in first. So I note that the density is 2200 and mass is 0.1 over V. So from here, you know that the volume is 0.1 over 2200, which gives me the answer 0.455. Okay, 0.0455 meter cube. Good, all good. So this is for density, and I'll see you in the next part of the video.